Hello, welcome to SC0X Week 3. This is our second week talking about optimization, and it's going to build upon everything we learned for constrained and unconstrained optimization using linear programming. And specifically, we're going to talk about four things. We're going to talk about integer programs, where we loosen the constraint that the variables have to be continuous. We're going to talk about mixed integer linear programs, where we combine different types of variables. Talk about network problems, where we work on a network because a lot of supply chain and transportation actually operates on a network. And then we'll talk about nonlinear programs. So let's start. First thing we're going to talk about is integer programs. And what happens here, it's just like a linear program where we have two decision variables, x1 on the horizontal axis and x2 on the vertical. And I drew in two constraints. And normally we'd say for a linear program, I draw my objective function and I know my solution would be in one of these corners. We learned that from last week. However, the restriction now, because it's an integer program, is that these decision variables can only take integer values. So what I'm doing here is drawing all the potential values that the solution could take. Now, it looks like that these 9 dots, it's fewer dots, so it looks like my solution space is getting smaller, but in fact, it gets harder. Because remember, for linear programming, we could leverage that corner solution, that property that all the solutions would be in a corner. That falls apart with integer programming. So now we have to actually look at each one of the possible solutions. So the big takeaway that you should take about integer programs is that they're very hard. They get much harder to solve. They take a lot more methodological horsepower. Next thing we're going to talk about is mixed integer linear programs, which has a lot of the same features here where we have integer variables, but we introduce a different type of integer variable known as a binary variable. Why do we do this? We do this because this allows us to make some logical conditions. Let me show you this through a simple example. So up here, I've got 3 plants. Each one of the plants produces a certain amount of product. X1, X2, X3. It's all the same. It's just being produced at different places, and you have to produce at least a certain amount, D. We could formulate this as a linear program very quickly. So let's do that. So that would be where I want to minimize, because I'm going to minimize costs. It would be the sum of C sub I. I assume there's some variable cost for producing these, times X sub I, subject to the sum of X sub I has to be at least a certain amount. So I want to minimize my cost, subject to the constraint that I have to produce enough to satisfy the demand. And also, I want to make sure what? That all the variables are greater than equal to 0. So X sub I greater than equal to 0 for all I. Piece of cake. However, in real life, there might be some other conditions, such as, what if I have a fixed cost for opening each of these? So it's not just a variable cost for how much I make, but if I open it, I have to pay something. I have to pay for the electricity, I have to pay for security, I have to pay for something that's independent of how much I produce. How would I capture that? Well, we know we do something in the objective function, and I would probably have something like summation of f sub I, but what would I multiply that by? Well, I need a new variable, and this is what's known as a binary variable. So we're going to introduce a variable called y sub I, and this is going to be equal to 1 if plant I is open, 0 otherwise, so any other condition. So my objective function is going to look something like that now, where I want to minimize the sum of the variable costs for everything I produce, plus the sum of the fixed costs for all the plants that I open. However, you're not done. And what we'll show in the lesson is how to link these together, because you need to have a condition such that if I produce anything out of a plant, I actually open the plant. Because remember, for this minimization of a math program, it'll try to lower the cost as much as possible. So how do we do that? Well, what we'll show you is that you'll have something like this. And this is known as a linking constraint. And so it's saying that all the volume out of xi for each of these has to be less than or equal to m, which is just a really big number, times y sub I. Now, it doesn't make sense to me now, but what this does, it forces a linkage. It actually forces the condition that if I produce anything of x out of a certain plant, I actually open the plant. It forces it to happen. It's known as a linking constraint. It's very powerful. It's kind of confusing the first time you do it, so we'll spend a lot of time on it. But what it allows us to do is to create a logical constraint that's known as an if-then. if I produce something there, I've got to open it. We can also use it for other things, such as an either or constraint, where I could either keep the plant closed, produce nothing, or if I do produce, it has to be above a certain level. So that's another condition that uses a linking constraint and some other constraints that we'll talk about. And the third one that we'll discuss is what I call a select from condition. Right now I have 3 here. What if I said you can only select 2 out of those 3? How do I select the best 2 out of the potential ones that I have? So in mixed integer linear programs, you have a lot of the integer programming complications, but we're going to introduce binary variables, which are very, very powerful, and they let you include logical conditions into your model. Then we're going to shift gears, and we're going to talk about networks. And networks are interesting because, as I said earlier, a lot of things in supply chains move on networks. It's not just physical distribution. You can think of financial flows. You can think of information flows. You can think of capital investments. You can put them into a network structure. So it's a very powerful framework. And networks simply consist of nodes and arcs. And so you could have this arc here, xij, which is simply the movement from I to node j. So we're going to talk about 3 problems in networks that are kind of the core of all the different network problems that you could encounter in supply chains. The first is known as the shortest path problem. So shortest path is simple. You start at one point. We're going to call that the starting node. And I want to find the shortest path to get to my terminal node. And so what we'll show you is you can formulate this actually as a linear program, but it'll determine what the shortest path is to that node from S to T. This is used in every routing system. It's kind of the basic network model that everything else rests upon. So the shortest path problem. Then we'll move on to the traveling salesman problem, which is probably one of the oldest problems that have been studied for many centuries. And what it comes down to, what the question is, how do I visit each and every node once and only once at a minimum cost? So the traveling salesman problem is core for any kind of vehicle routing problem, any last mile delivery. Think of any postal service or anything that goes to many stops. So what we'll do is we'll show how to solve this problem, not optimally because it gets very hard very fast, but we'll introduce heuristics. And what heuristics will do is they'll show a quick way to get an okay solution. So we'll talk about different heuristics that you can use for this problem, just to introduce the concept of heuristics. Finally, the third network problem we're going to do is flow problems. And specifically, we'll look at what's known as the transportation problem and the transshipment problem, but they all boil down to the same thing. I have a bunch of suppliers here, the squares, and they ship product to these distribution centers or transshipment points, the triangles, who then ship the product out to the different customers. And there's different options of which DC serves which customer and all of this. And what we want to do is figure out what's the best flow of product from the suppliers all the way down to my final demand of my customers. How do I minimize the cost of that flow? All right, so that's what we'll talk about for networks. The last thing I want to talk about in this lesson for this week is nonlinear programs. So again, down here we've got the classic decision variable of x1 and x2, and so we want to solve this, and so we could have even a constraint that looks something like this that's linear, right? But what if my objective function is nonlinear? What if it looks like something like this? You can see probably why this makes it difficult. So if this is my objective function, right, my objective function, where's the optimal solution going to be if I'm maximizing? Well, it's not going to be at one of those corners, which linear programming is so good at and so efficient. It's actually going to be somewhere here. So by having nonlinear objective functions or constraints, make the problem, again, much, much harder. So these become very hard, and there's special techniques that you can use to try to solve those types of problems. Okay, so this is what we're going to talk about in week 3. It's a lot of material, but I mainly want to expose you to it so you understand the main concepts behind it. In later courses, we'll go much deeper into some of these different problems because they apply to different aspects of supply chain management. So I hope you watch the videos, hope you enjoy those. Watch the recitation videos, try the quick questions, the practice problems. Make sure you understand the concepts. Have fun.